Welcome back to Dave Does Math from Home. We're doing section 17.1, vector fields. This is part 2. Part 1 cut pretty abruptly. Sorry about that. The file storage system on this particular memory card is not good, and there's a maximum file size. So sometimes the camera just truncates the video and then starts a new one. But I said most of the things I wanted to say in the last video. So now we can do new stuff. I still want to keep doing some examples of vector fields. So I want to talk about one of the most basic vector fields there is. F of xy equals x, comma, y. So again, we're going to do the 9 grid points that I really like, and if we draw those and we want more, we can add some more. I'm going to go 0, 0, 0, 1, 0, negative 1, 1, 1, 1, 0, 1, negative 1, negative 1, 1, negative 1, 0, negative 1, negative 1. The order is kind of goofy here, but I'm getting lazy about trying to do it all around. So we're just doing the 3 that are on the y-axis, the 3 that are to the right of it, and the 3 that are to the left of it. These are the 9 points that I like to do. As usual, the point 0, 0 is going to give us the vector 0, 0. That happens sometimes. This is going to give us the vector 0, 1. This is going to give us the vector 0, negative 1. This is going to give us the vector 1, negative 1. This is like the easiest thing to write down because they all just, the vectors, these two numbers in their same order. This will give us 1, 0. This will give us 1, negative 1. This will give us negative 1, 1. This will give us negative 1, 0. And this will give us negative 1, negative 1. Okay. Negative 1. Okay. So we'll come over here and we'll start drawing it. Okay. Point 0, 0 gives us the vector 0, 0. Point 0, 1 is here. It's going to give us the vector 0, 1, so that's going straight up. 0, negative 1 is going to give us the vector 0, negative 1, straight down. 1, 1 is going to give us the vector 1, 1. That's straight out. 1, 0 is going to give us the vector 1, 0, straight out. 1, negative 1 is going to give us the vector that goes straight out. Negative 1, 1 is going to give us the vector that goes straight out. Negative 1, 0, straight out. Negative 1, negative 1, straight out. These should all be approximately the same length. I guess the diagonal ones are a little bit bigger, about 40% longer. This is the vector field where everything moves exactly away from the origin. And the strength with which it moves away from the origin is relative to how far away it is from the origin. So things that are already far away go further away, and things that are really close, they just kind of don't move much. I think the official name for this vector field is called the radial field, because it sort of like radiates outward. I like to call this a variation of the explosion field, because it kind of looks like an explosion, like everything in the middle is going outwards, straight outwards. Much like the toilet flush, this is not actually a spectacular representation of an explosion, because in an explosion, the things really close to the origin would be moving the fastest, and the things that are far away from the origin would be moving less fast. So we could change this like, I think the proper explosion vector field would be like x comma y divided by x squared plus y squared. So if you divide by essentially the radius, the distance from the origin, that makes these ones that are far away, it'll make them smaller, it'll make these ones that are really, really close much, much bigger. It actually gives you sort of this asymptotic behavior where, like, at the origin, things would be moving with infinite force. So again, not a perfect model, but yeah. This is the better way to model an explosion in 2 dimensions, which is probably why this one is officially called the radial. But I think this is explosion-like, so everything goes out, away from the origin. So this is a good one. You'll see this one a lot. What else should we do? Let's try something like, nope, not like that. Let's try something like f of x, y equals, let's do 1 comma 2 minus y. Let's see what this does for us. I'm going to use the same standard set of 9 points. And we'll start with 1, 1, 1, 0, 0, 0, negative 1, negative 1, negative 1. And then we'll do 1, 0, negative 1, 1, 0, negative 1, and 1, 0, negative 1. That's a good way to organize my set of 9 points. At 1, 1, this should give me 1 comma 1. This should give me 1 comma 2, and this should give me 1 comma negative, or 3, it is. And here's what's neat. This vector field does not depend on x at all. So when I change these, when I use the same set of y values with the new set of x values, this vector field doesn't change. It's going to be 1, 1, 1, 2, 1, 3. Because there's no x's involved in this. So using a new x value should give me the same set of 3 coordinates. And the same down here as well. 1, 1, 1, 2, 1, 3. So let's see what this thing looks like. At 0, 0, I'm going to get the vector 1 comma 2. So it's going to be doing one of these. Let's go. If I change the x value to get negative 1, 0, 1, 0, I'm getting the same vector. Let's look at what's happening above. When y equals 1, so that's this point, and this point, I'm getting things like this. When y equals negative 1, at these 3 points, I'm getting things that are very tall. All 3 of these vectors point towards the line y equals 2. If we were on the line y equals 2, we would get vectors that were flat. If we were above the line y equals 2, like if we started doing this with y equals 3, we would get vectors that pointed down. Everything flows towards this line, y equals 2. It's bigger. comes this way. So this is, I think, a really good way to model things converging to this line. So I mentioned earlier, the first example we did, we had this sort of crisscross pattern where I said things were going this way. Now things are going this way. Everything is always moving to the right with this much force or this much speed or this much velocity or whatever this thing represents. And everything is moving vertically, everything is moving towards this line. So this is a neat vector field. It's a nice way to model convergence like that. I'm trying to do convergence. Some kind of convergence thing happening there. This is handy. I don't think this one has a name. I don't think we need to give it a name. I think that's probably enough of me doing examples of vector fields. I want there to be some surprises left for you as you do the homework and discover some vector fields of your own. You know how to create a table to get a list of vectors. You know how to graph those vectors. You can play with these vector fields and make them up as you go. So that should be good there. There's one other thing we need to talk about, and that is determining when vector fields are perpendicular to certain curves and when vector fields are tangent to certain curves. I won't say the word parallel. Tangent is the right word to use here because curves aren't straight and vector fields aren't straight. But I want to do that in a separate video so that it's all very self-contained and we don't start something and have to finish it in a different video. So we're going to cut this one right here and I'll start part 3 henceforth.